This video will cover some basics about waveguide practical applications and hopefully demystify the theory of operation. The electromagnetic textbooks show the equations for all the modes possible in waveguide. In the industry, only one mode is in dominant use generally. Hopefully this video will help you understand waveguide operation intuitively. What is waveguide? Waveguides are perhaps the most efficient way to transfer electromagnetic energy. They are fundamentally coaxial lines with no center conductors. Rectangular, round, and elliptical-shaped waveguide have been used and studied. Rectangular waveguide has the widest usage in the industry. The waveguide concept was proposed by J.J. Thomson in 1893 and was experimentally verified by O.J. Lodge in 1894 using electromagnetic waveguides. The mathematical analysis of the electromagnetic propagating modes within a hollow metal cylinder was first performed by Lord Rayleigh in 1897. You should do an internet search on Lord Rayleigh. He was a most brilliant engineer. The takeaway from this should be a phrase that I picked up many years ago. Be modest. A lot was accomplished before you were born. There are many advantages to using waveguide. First of all, it's completely shielded. However, care must be taken in selecting the right waveguide parts for flange connections. Waveguide is the lowest loss method of transmission for RF energy. Coaxial cable center conductors have very little surface area, so they are lossy due to skin effect. Waveguide has a large surface area for high conductance. Waveguide also has a low dielectric loss, as the dielectric is usually air. Often, the impetus for using waveguide is power handling capability. Some waveguides can handle up to a megawatt of power if filled with a gas. It also has excellent phase stability due to its rigid structure. The obvious disadvantage of waveguides are weight, large size, and it is more expensive than coax cables. Most electromagnetic textbooks quickly dive into the mathematical theory of waveguide. They generally study the myriad of waveguide modes, which can be an academic exercise. You will see page after page after page after page of math. While we won't get into all that math, the designator of modes should be explained. In the transverse magnetic mode, the entire magnetic field is in the transverse plane and has no portion parallel to the length axis. In the transverse electric mode, the entire electric field is in the transverse plane and has no portion parallel to the length axis. This two-letter designation has a subscript. In the example of TE10 mode, the first subscript is 1 since there is only one half-wavelength pattern across the broad wall. There are no E-field patterns across the narrow wall, so the second subscript is 0. In most practical applications, the dominant or TE10 mode is used. Most textbooks are so mathematical and theoretical, they don't depict the theory of operation very well. Here is a way to visualize the waveguide operation in its dominant mode. Let's start with a ground plane, now putting down some insulators. Then a wire connected to a row of insulators. Then put down another row of insulators and another wire. I believe we can all realize a 2-wire transmission line with an insulator between the wires and the ground plane. We can add as many insulators along the wires as we want, and it is still a valid transmission line. At a single frequency, a stub that is a quarter wavelength long can be connected from either wire to the ground plane and become a very high impedance. Imagine a sine wave with a frequency of which a quarter of its wave is what it takes to travel down the length of the stub. It hits the short at the end and the wave is reflected back up the same quarter wavelength. This is a half wave round trip. At that point, the voltage is opposite of what it was to start with, which is 180 degrees out of phase, and it cancels out. Ponder the concept of this as a metallic open. At frequencies above and below this quarter wavelength, the signal is shorted by the stub, and the power is reflected back to the source. This quarter wave stub insulator, just like the two-wire transmission line standoff insulators, can be placed anywhere on the transmission line and still be a valid transmission line. Now you can begin to visualize the rectangular shape of a waveguide with the narrow wall being ground and the conductor being a portion of the broad wall. Now let's lay that structure down on its broad side. This visualization allows us to think of the conductors inside the waveguide structure as bus bars. The waveguide is formed by a continuous layer of quarter wave metallic insulators depicted by the thin lines. These bus bars are inside the waveguide only. Because of skin effect at high frequencies, the current only flows on the surface of the metal. The outside of the waveguide is still ground. From here on, we will refer to the current carrying surface inside the waveguide as bus bars. There aren't any bus bars inside there for real. It's just an abstract concept. Let's talk skin effect. In electromagnetics, skin effect is the tendency of an alternating electric current to become distributed within a conductor such that the current density is largest near the surface of the conductor and decreases exponentially with greater depths in the conductor. It is caused by opposing eddy currents induced by the changing magnetic field resulting from the alternating current. The electric current flows mainly at the skin of the conductor between the outer surface and a level called the skin depth. Here is the formula for skin depth. Delta is the skin depth in meters. Rho is the bulk resistivity of the material. Mu naught is the permeability of free space, which is 4 pi times 10 to the minus 7th henries per meter. Mu sub r is the relative permeability of the material, which is usually 1, and F is the frequency in hertz. Here's an illustration showing the skin depth of a round conductor. Since the current density falls off exponentially, some standard of measurement is required. Skin depth, delta, is defined as the depth where the current density is 1 over E, or about 37% of the value at the surface. Here's a chart showing the skin depth in micrometers across a wide frequency range for aluminum and copper. The resistivity of copper is lower than aluminum, so the skin depth will be lower as well. A rule of thumb is that the depth of the medium should be 5 times the skin depth. Waveguide does not operate exactly like a two-wire line that is completely shunted by quarter wave sections. If it did, use of the waveguide would be limited to a single frequency. A fairly small range of frequencies of somewhat shorter wavelengths can pass efficiently. Here's an illustration showing the quarter wavelength at lower frequencies. The bus bar is thin. Now for shorter wavelengths, the bus bars are wide. Nice wide bus bars mean low loss. There is a standardization of waveguide sizes. This was done in World War II. The designation for standard sizes begin with the letters WR, which you can guess stands for waveguide rectangular. The number following that designator is the broad wall width in 1/100ths of an inch. The A dimension of WR340 is 3.4 inches. 3.4 times 100 is 340. Let's take a look at the biggest waveguide. It's intended to work between 320 MHz and 490 MHz. The broad wall is a whopping 23 inches. Also note the wall thickness is 150 thousandths. Since the skin depth is deeper at lower frequencies, a thicker wall is necessary so there is no current flow on the outside of the waveguide. Also notice most of standard waveguides have the narrow wall dimension 1/2 the width of the broad wall. In a few cases, this is not true. I've been told that in World War II, a chair manufacturer was making their chair features out of rectangular extrusion. It was so prevalent and available, a few of the standard waveguide sizes were born from these chair materials. Those are the few waveguides whose narrow wall was not exactly 1/2 the dimension of the broad wall. This is the chart continued to the smallest waveguide. At a frequency range of 140 to 220 gigahertz, the broad wall is only 51 mils. The charts also include the cutoff frequency. Let's discuss waveguide and cutoff. As the frequency decreases, the bus bars become thinner. At some point, obviously, the bus bar will go to 0. It should be obvious that happens when a quarter wavelength is half the width of the broad wall A. This is called waveguide and cutoff. So what frequency is it? Another quarter wavelength is the distance across the whole width of the broad wall, which is half the wavelength. A full wavelength would be 2 additional quarter wavelengths, so the full wavelength would be 2 times A. The cutoff wavelength is lambda sub c, which is 2A. The speed of light, c, is the wavelength times frequency. Replacing lambda with 2A and rearranging to solve for frequency gives us this. Let's look at an example for WR75 waveguide. Its broad wall width A is 3/4 of an inch. That's 0.01905 meters. Plugging that into our equation gives us a cutoff frequency of 7.869 gigahertz. What happens at the high frequency end? As frequency increases, there becomes more than 1/2 wave in the electric field of the broad wall. The waveguide will now operate in a higher mode, which would be the TE20 mode. The TE20 mode is sometimes used to minimize loss, but the waveguide must be twice as broad as used in the TO10 mode. What size for the narrow wall, or the B dimension? The narrow side size matters for power handling. It depends on the breakdown of the dielectric. It is usually air, but sometimes liquid or gas is used to improve power handling ability. B is generally 0.5A. Half-height waveguide is sometimes used where the power is low and the desire to reduce weight is a key concern. Here is the general equation for loss in a waveguide. It is specifically for copper rectangular waveguide. A and B are the waveguide dimensions, F sub C is the cutoff frequency, and F is the frequency of interest. The resultant attenuation is in dB per foot. The attenuation is only the loss due to the conductor. If the waveguide were filled with an insulator, the loss could be greater. I got this equation from this 1948 book. I would venture to say measurements were taken, and this is a curve-fit solution for the measurements. For other materials, simply multiply this loss by the square root of the ratio of the material's resistivity relative to the resistivity of copper. The resistivity of copper at 20 degrees C is 17.2 nano-ohm meters. The resistivity of 6061 T6 aluminum at 20 degrees C is 39.9 nano-ohm meters. Therefore, aluminum has 52% more loss than copper. If you look up properties of aluminum, you will probably find the resistivity of aluminum to be around 26.5 nano-ohm meters. Aluminum alloys like 6061 T6 are widely used and has a significantly higher resistivity than pure aluminum. By the way, a nano-ohm meter is a very small ohm meter. Here is a chart of the attenuation of aluminum WR75 waveguide. What is the band of frequencies we operate with reliably? Let's look at the attenuation of the aluminum WR90 waveguide. You may be tempted to operate near the cutoff frequency where the attenuation is not degraded very much, in this area right here. It turns out the group velocity is very degraded in this area. Here's the equation for group velocity. Group velocity in a waveguide is the speed at which the electromagnetic energy travels in the guide. Here is a chart of the group velocity versus frequency of the WR90 waveguide in percent relative to the speed of light in free space. The microwave gods determine that you should not operate below 60% of the speed of light. In this plot for the WR90, it comes out to 8.18 gigahertz. If you ratio that to the WR90 cutoff frequency, you get 1.25. So to establish the minimum operating frequency, simply multiply the cutoff frequency by 125%, which yields 8.2 gigahertz. Now for the high frequency limit. If operating too high in frequency, you run the risk of skipping into the TE20 mode. Again, the microwave gods declared that the upper frequency to be equal to or less than 189% of the cutoff frequency. In this case of the WR90, that comes out to be 12.4 gigahertz. Therefore, the acceptable operating band for WR90 is 8.2 to 12.4 gigahertz. And here it is in the chart. So far, we have only talked about rectangular waveguide stock. There must be a way to connect various sections of waveguide and waveguide components together. This is accomplished with flanges. The problem is, you really need a good connection across the bus bars. You can see how mounting flat flanges together with screws could result in a less than desirable connection. The flange face would need to be perfectly flat. The torquing of screws can cause the flange to oil can. This animation depicts that scenario. This will result in the separation of the bus bars. This is an exaggerated illustration, but hopefully you get the point. To eliminate the issues with using two flat flanges mounted together, the choke flange was invented. It uses a half-wave short approach to improve performance. It is accomplished by milling or electrodischarge machining slots on the flange face. For quality connections between the waveguides, a choke flange should be used to mount against a flat flange. This is a cross-section of a choke flange mounted against a flat flange. This surface, as you can see, is not flush with the flat flange. This configuration allows for 2 quarter-wave slots to make a half-wave stub. Consider a sinusoid. The wave will travel down through the 2 quarter-wave sections. Assume it starts at VO plus and travels down to VO minus. It hits a short and is reflected. The half wave travels up at VO plus, which results in a full wave round-trip reflection. At full wavelength, the reflected wave will be 360 degrees out of phase and will effectively be a short, since VO plus and VO plus do not cancel. We described earlier the concept of a metallic insulator. Conversely, think of this as the concept of an air short. Another attractive feature of the choke flange is that it facilitates a gasket. The conductive gasket is needed to seal the stub features from leakage. It also makes a nice environmental seal. It's usually a simple conductive O-ring that lays in the outermost groove. Notice the vertical stub varies in length across the circular geometry with relation to the broad wall. This results in a small VSWR that will increase, if not quarter wave. Some flanges have rectangular vertical stub features instead of circular to mitigate this effect. There must be a way to get a signal to and from a waveguide using a cable. This device is called a waveguide to coax adapter. The coax connector extends the center conductor down into the waveguide from the broad wall. This acts as an E-plane probe. The back end of the adapter is called the back short. The probe is placed a quarter wavelength from the back wall of the adapter so that the wave reflected off the back wall cancels out, just like our quarter wave insulator concept. It's nearly impossible and impractical to make waveguide systems that can be manufactured in one piece. To route waveguides at right angles, waveguide bend components are made to facilitate this. There's an easy way to remember which bend is which. The E-plane bend is bent the easy way, and the H-plane bend is bent the hard way. Here are some pictures of some various waveguide devices. A power divider can be made from a T construction. Here's an E-plane T. If the signal is input in the middle, one side of each T will have the signal 180 degrees out of phase with the other. In the case of the H-plane T, the signals will be in phase with each other. The magic T is a hybrid version of the H-plane T, where an E-plane section comes out the middle. The magic T is sometimes used as a duplexer. It's a cool sum and difference device. The name magic T is derived from the way in which the power is divided among the various ports. A signal injected into the H-plane port will be divided equally between ports 1 and 2 and will be in phase. A signal injected into the E-plane port will also be divided equally between ports 1 and 2, but will be 180 degrees out of phase. If signals are fed in through ports 1 and 2, and they are added at the H-plane port and subtracted at the E-plane port. Waveguides also make good couplers. The broadwall coupler has the most bandwidth. Two waveguide sections are brazed together with an array of holes leaking RF from the main guide into the coupled arm. The pattern of the diameters across the length of the arm are usually a Bessel function. This is a cross-guide coupler where one side of the coupler port has a waveguide termination. A waveguide termination is generally an ohmic pyramid with the base of the pyramid at the closed end of the structure. Thanks for watching. Please click the like, subscribe, and notification bell so you don't miss any upcoming content.